Start, Tobias Hansen is going to talk about bootstrapping things.
Okay, thank you very much. I'd like to thank the organizers for inviting me to come here and to give this talk. And this talk is based on, by now, 5 papers that I wrote with Fernando Alday and Joao Silva. And it's about trying to bootstrap the Virasoro-Shapiro amplitude in ADS5 cross S5. And our motivation is that type 2b strings in ADS5 cross S5 being probably the most studied example of the ADS-CFT correspondence, the worldsheet theory is still not fully understood. So we would like to understand the worldsheet theory of this string theory. And in particular, a good first step would be to compute the 4-point tree-level amplitude. And this amplitude has an expansion in alpha prime, the string length squared, divided by the ADS radius squared. And then we write the corrections as AK. So the goal is we would like to bootstrap this curvature corrections to the Virasoro-Shapiro amplitude using properties of the worldsheet theory and the dual boundary CFT, n equals 4 super Young-Mills. So let's make a plan. So step 1 will be we make an ansatz, and we want to use that this amplitude is a genus 0 closed string amplitude. So we expect that AK has a representation as an integral over the Riemann sphere. So we have, as in the flat space case, we have this powers 2s minus 2, where s is a dimensionless Mandelstam variable containing a factor alpha prime. And then we have 2t minus 2. And then here we expect there is some worldsheet correlator, which can depend on s, t, and z. And the first property of this worldsheet correlator is it has to be a single-valued function because it is a CFT correlator on the Euclidean slice. So in Euclidean signature, when you move one operator around another one, there can be no monodromy. So this function has to be single-valued. To give you some orientation in flat space, if we demand this to be manifestly crossing symmetric, it's just 1 over u squared plus this plus this. So this is a for graviton amplitude, but in this case there's a factor where polarization is stripped off. So it just depends on S and T.
But which CFT is this correlator in?
This correlator would be the worldsheet CFT of the string.
Well, what does this mean?
I mean,
is it known that this CFT exists? Because sometimes, you know, when string theory, I just recall vaguely that in the early days of ADS-CFT, there was a long discussion that because of the Ramon fluxes, there is not really any CFT. You cannot think of this theory as CFT, separate CFT and separate gravity. Like there is some unavoidable mix between worldsheet gravity and worldsheet CFT because of picture changing operators and whatnot.
yes.
And so but I don't recall how that discussion
Okay, I cannot
concluded.
promise you that this is really, strictly speaking, a CFT correlator.
Yeah.
But I will give you exactly how this is related to the n equals 4 super Young-Mills correlator. We make an ansatz and we will make checks. So, yeah.
Slava, what you're saying is expected to be true to be the case in NSR formalism, but you know, the thing here, I don't know if Nathan Berkowitz is going to tell you that there is a pure spinner formalism. In the pure spinner formalism, there is a construction of the worldsheet theory. It is 5 times S5. I think that there is a standard recipe that one can follow to compute this correlate in that formalism, at least perturbating alpha prime.
Okay, can I ask you a question? So, but this ansatz, is it obvious that given the worldsheet it has to be of this form, the dependence on S and T, the way it appears, or in a way, actually, sorry, now that I look at it, why did you split this prefactor? Because everything, I mean, if G depends on S, T, and Z, you could also absorb the prefactor, right? It's just for convenience.
Yeah, this is like the scaling, takes care of the scaling of the correlator. Historically, we first computed the Wilson coefficients, and then we found that there's such a formula reproducing the Wilson coefficients we already computed. But yeah.
Maybe we should let you proceed because you have, but at this point, of course, this formula is always true because you haven't told us what G is, right?
Yeah.
So any function A can be written in this form.
Yeah. So,
but S and T are going to be the Mellin variables, or what are they? Because we are looking at the correlation function in CFT. Right?
They are related to the Mellin variables by a Borel transform.
Okay, thanks.
Yeah. So first, I will present you like a kind of string toy model. So this is not the complete string theory. This gives you one contribution to strings in ADS, and the only purpose of this is to give us some intuition what kind of functions should appear in this function G. So step 2 is fix the parameters of the ansatz. And to do this, we will use dispersive sum rules in n equals 4 super Young-Mills theory. And then step 3 is, once we have fixed this, we can compute some data and check that we get the same data as what's available from integrability and localization. And we did this for k equals 1 and 2. So this was successful. So let's start with this string toy model. And we will completely forget about supersymmetry. We will just use the path integral for the 4-point amplitude in the bosonic string. So there's some field X and the worldsheet metric G, the Polyakov action, and 4 graviton vertex operators. Yeah.
So the check at the k equals 1 and 2, if I remember correctly, probably doesn't get to the order where you encounter ambiguity is not fixed by nonlinearly realized supersymmetry of the Green-Schwarz action, right? I mean, in principle, everything should be fixed by integrability, but I think that the thing that's sensitive to integrability, I forgot exactly which order in alpha prime, but probably higher than k equals 2.
So we check against the anomalous dimensions of single trace operators on the leading radial trajectory at order lambda to the minus 3/4.
I'm just saying a very basic thing, which is that if you didn't know about like pure spinor formulas or anything like that, if you just try to build the worldsheet theory using the effective action, namely in the Green-Schwarz formalism, you would encounter potentially ambiguities of higher derivative terms at some order in alpha prime expansion. So if you do, the usual alpha prime perturbation theory in Lycombe gauge or something, you're running into ambiguity in the counter terms. I don't quite remember which order you would encounter, but I think probably higher than k equals to 2. So it's just a comment. I'm not saying it's trivial, but I'm saying that it's more than trivial when you
Yeah. Okay. So we will use the Polyakov action in ADS 5 cross S5. So this is, so we have this worldsheet metric. And then here we have the target space metric, which will be ADS. And this will have an expansion around flat space. So we have flat space metric plus some radius corrections, where these corrections are proportional to x mu, x nu. And this we can write as two derivatives acting on this exponential. And then we take q to 0. And if we insert this here, we see that this is the flat space action plus this operator where we take the momentum to 0 and take two derivatives acting on a graviton vertex operator of q, because we have this exponential inserted here, then it becomes a graviton vertex operator. So that tells us that if we want to know the kth curvature correction for the 4-point amplitude, this gets one contribution from a flat space 4 plus k graviton amplitude, where we take the k of the momentum to be very soft, and with this with this derivatives acting. Since we do this k times, we have d. So q are the momenta of all the soft gravitons, and we have 2k derivatives. So what is this? For the leading terms, we can use the soft graviton theorem to figure out what is this amplitude with k soft gravitons. So we have 4 plus k, so where p are the usual momenta and all the others scale to 0 with some parameter epsilon. And the soft graviton theorem tells us that the leading term will go like, if you take one graviton to 0, will go like 1 over epsilon, some constant term times the amplitude with one graviton less. So it goes like 1 over epsilon to the k, a0 to the 4. And then the subleading soft graviton theorem depends on the angular momentum operator. So this is linear in derivatives of momentum. So we have something like 1 derivatives of the remaining momenta of A4. And if we act with this derivative on these, first of all, since we take 2k derivatives, what we're really interested in are the term of order epsilon to the 2k, because this is the one that will be finite. And we expect when we do the full computation in the supersymmetric theory, all the divergent terms should cancel. So now we can insert the 4-point amplitude, so it's like so the leading term will be just 1 over epsilon to the k. Now if we act with these derivatives on these exponentials, we get a log of absolute value z squared, or a log of absolute value 1 minus z squared. And these are precisely the single-valued multiple polarity logarithms of weight 1. And you can do this computation for a few more orders using not the soft theorem, but the explicit flat space amplitudes. And you can see that at order epsilon to the 2k, there will be single-valued multiple polylogs of weight 3k. So the weight just increases by 1 for every order in epsilon. So the conclusion of all this is that the maximum transcendentality at this order should be 3k, and we will assume uniform transcendentality. So we will have single-valued multiple polylogs of weight 3k. Okay, now I should tell you what are single-valued multiple polylogs. And to this end, I first have to tell you what are the usual multiple polylogs. So these are functions given, they are labeled by a word. So I will call this W. And the letters in the word are from the alphabet 0 and 1, because our worldsheet correlator has singularities at 0, 1, and infinity. And this is given by an iterated integral. And then the first one is just 1. So some examples, if we have p zeros, this gives log to the p. If we have p ones, it gives log to the p of 1 minus z. And for example, if we have p minus 1 zeros and 1 1, it gives the polylogarithms the p. And if we evaluate these functions at 1, they give rise to the, so if we set z equals 1, we get multiple zeta values. So what are then single-valued multiple polylogs? So these were constructed by Francis Brown, and they are weight-preserving linear combinations of such products of multiple polylogs of z and z bar in such a way that these functions are single-valued and satisfy the same differential equations as these multiple polylogs. Because of this equation, you can also derive differential equations for them. So for example, if we have the single-valued one with p zeros, we get log to the p of absolute value of z squared. For p1s, we get the same with argument 1 minus z. And if we get, for example, 0, 1, we get some complicated combination. Yeah. And if these are evaluated at z equals 1, we get single-valued multiple zeta values. This is something that we used in some of the papers. These single-valued multiple zeta values form a smaller space of numbers than the usual multiple zeta values. Okay, so much about this. Any questions so far? Yeah.
Just not to get too lost. So here you're saying you computed in the bosonic case, and you have reasons to believe that this set of functions is valid also in the supersymmetric case, or it's just by analogy?
In the bosonic case, we would always expect these functions and any lower transcendentalities. And in the supersymmetric case, we say we assume only the maximal transcendentality. We assume uniform transcendentality.
Why is that?
I mean, this often happens in maximally supersymmetric theories, like n equals 4, and in the end, we only know that in the end we have our checks, you know. So,
Okay, and also about the divergences here, is it easy to understand why the bosonic theory should not be well defined? I mean, I know the bosonic theory in general is not well defined, but here, why do you get infinity instead of a finite?
I mean, for example, this first term is always 0, even in this computation. So I'm just not checking in detail how many of them vanish.
So you would expect them to vanish also in the bosonic case?
I mean, in this toy model, no.
Okay.
Like I think the first 2 vanish and then not, but in the full model, I would.
Okay, thanks.
Yeah. Okay. So let's now go to the boundary CFT and become more concrete. So the correlator. So we are working with with weak string coupling and in an expansion alpha prime over r squared. This is our regime we're working with, and then in n equals 4 super Young-Mills, this corresponds to large n and large coupling. And in particular, we will study the correlator of 4 operators O2, which is the superconformal primary of the stress tensor multiplet. And the first thing we use is the superconformal Ward identity. Which fixes this correlator up to a function of the 2 cross ratios u and v, which is the reduced correlator. Then we take the Mellin transform of this function in u and v. This gives us a function in terms of s and t. And finally, we will also take the Borel transform of this. Given by this formula. And then we will expand this in large lambda. So we get A is the sum over K. One was. And this is the function AK we will be studying. So this is, of course, just the flat space limit of Joao at the first order. But we are not taking the flat space limit. We are not taking the radius to infinity. We just take this as an integral transform. And the k equals 0 term will be the flat space Virasoro-Shapiro amplitude, where the factor with the graviton polarizations is stripped off because we study this reduced correlator. Okay. So let's talk about these dispersive sum rules we will use to constrain our this amplitude. Okay, so first of all, before we write them down, we have to define the low energy expansion. This makes contact with the low energy effective action of the string theory, and it's an expansion of this amplitude in terms of tree-level diagrams, so the supergravity diagrams and quartic contact diagrams. And I will write it down right away for this function A. So it's so there will be a sucra term And then there will be this expansion in crossing symmetric polynomials. And then here we have the Wilson coefficients. So there's a similar formula for the Mellin amplitude that can be obtained term by term using this transformation. And the dispersive sum rules are derived using two ingredients. One of them is that the poles of the Mellin amplitude depend on the OPE data.
So, sorry, Tobias, I'm confused. I thought the supergravity would be the leading term in like the k equals 0 term or something like that. Right? You're saying it appears contributes
the
to every
supergravity of the Mellin is something like this. And the reason it appears also for other Ks that this is not homogeneous in ST and U.
I see. Thank you.
So it appears for k equals 0, 1, and 2, and then it vanishes because of there are no poles to pick up from this integral. So
Thank you.
okay, so we have the poles. So here we have the Mach polynomials. And this OPE data is always the superconformal OPE data because we use the superconformal block expansion of the reduced correlator. And the second ingredient is the bound on chaos. That tells us that for large S, the Mellin amplitude is bounded by S to the -2. So for the -2 is because of supersymmetry. We get 4 factors of S from supersymmetry. For standard Mellin amplitude is S squared. And we use this to write a dispersion relation where the arc at infinity vanishes because of this. And in the end, the dispersive sum rules can be solved for the Wilson coefficients. So we get expressions for the Wilson coefficients as a sum over single trace superconformal primaries. And then here we get some explicit functions of the OPE data. Single trace is because the poles of the double trace operators are contained in the measure of the Mellin transform. So we get we get only poles for single trace operators. So now let us discuss the spectrum. What are these operators here that appear in the dispersive sum rules? So the answer is from the ADS-CFT dictionary, we see that these are supposed to be massive strings. So from the ADS-CFT dictionary, the dimensions go like lambda to the 1/4, 2 square root of delta, where delta is the flat space string mass level. And then we get corrections of this order. And because of the symmetries of our correlator, we will have operators of even spin only and 0 R charge. And in one of our papers, we computed the degeneracies of these operators. So you can make so the labels are the same as in flat space, mass level delta and spin L. And then we can, so we have mass level 1, 2, 3, 4, 5, and spin. So on the leading Redshift trajectory, these operators are non-degenerate, so we get always 1. The next one we get 2, 4, and then it saturates at 6. And then we get some more, grows pretty quickly, 40, 99. So this is the leading Reddit trajectory. This is the Konishi operator, which at recoupling is like trace phi I. And 2 weeks ago there was a paper by Gromov, Hegedus, Julius, and Sokolova, where they computed the dimension of some of these operators using the quantum spectral curve, and they found all these operators up to mass level 3 by starting at recoupling and following the dimensions up to strong coupling, and at leading order they found these numbers of operators with this leading dimension. For the higher mass levels they didn't study enough operators to find all of them. Now, how does this OPE data look like? So, and how does it appear together with the Wilson coefficients in the sum rule? So we can label all the OPE data by these delta and L. And we have that this one goes like lambda to the 1/4, delta 0, and then and the same here. And then this data appears together in one dispersive sum rule. And also this data appears in another sum rule, and so on. And here we can just solve for this, take the flat space Virasoro-Shapiro amplitude, compute these Wilson coefficients.
I have a dumb question. Why are there these degeneracies? Why are all these scaling dimensions the same? Alternatively, why is delta an integer?
So what we did was we took the flat space string spectrum, which comes in representations of SO9, because it's massive particles. Then we broke the symmetry according to ADS5 cross S5 into SO4 times SO5. And then the SO5, you have to do Kaluza-Klein reduction, count all the Kaluza-Klein mode. From this branching in Kaluza-Klein, this becomes more states in flat space. In flat space, there are just ones everywhere. Yeah, it's because we label everything by flat space labels. So, yeah. So the first box, everything is known from flat space. And here in the other boxes, these dimensions are known from integrability on the leading Reggio trajectory. And two of these Wilson coefficients and also two of these ones were known from localization. So this will be the data we can later use to compare to. So how do we use now this dispersive sum rule to fix coefficients in our ansatz? What we will do is we will sum the low energy expansion. So in these formulas that we have, the dependency on A and B is explicitly known. So we can just plug it in, sum over A and B analytically. This will make the poles of explicit. And then we can compute the residues at S equals delta. And then we can also compute the residues from the worldsheet formula, equate both, and fix the parameters of an ansatz. So first of all, we want to go from the dispersive sum rules to the residues. So we sum the low energy expansion and expand S equals delta, which is a positive integer. And what we get is that there are poles, and the highest order pole is of order 3k plus 1. And this residue depends on T, delta, and only on the flat space OBE coefficient. the one that comes from the flat space Virasoro Shapiro amplitude. And then the residues depend on more and more OPE data, and the final pole depends on T, delta, the flat space OPE data, but then also on all the other OPE data at that order. So there will be delta K and up to C square K plus regular. So in a sense, this is what gives us the power to solve the ansatz, because a lot of residues are fixed by OPE data at lower orders in the expansion. So OPE data.
Sorry, Tobias.
Yeah.
So I have some intuition for the analytic structure and the poles in the melon, but I don't have so much after this Borel transform. So what is the expected analytic structure? Where are the poles in this after you do the Borel transform?
So there are poles at the, I mean, it's become something like the flat space amplitude, and these are the masses, right?
So you mean you have poles at deltas, but where you remove this lambda to 1/4? Is that the only thing you do? Or? No, but not even that.
So it comes, I mean, if you plug in the A and B dependence of this and do the sum, you just, at expand, you just get this.
But let's say a priori,
Yeah.
from what we know from Mellin, we know the poles are at the dimensions of the operators exchanged.
Yeah.
Then we do this Borel transform. We still expect some meromorphic function after the Borel transform, or what kind of function do you expect? Doesn't look like.
Yeah, I think at trivial level we would still expect a meromorphic function. And we see this by doing the sum. And we expect poles at the masses of the particles that are exchanged. How we do the sum?
Yeah.
Basically, I mean, there are some, it's quite a complicated dependence, but we can compute analytically like the generating series for these coefficients depending on A and B. So it's just, yeah, without showing details, I think I cannot explain it.
But I mean, are you stratifying, maybe summing some, I don't know, monomial with the same powers and so on and so forth, or just doing that sum? You have a double sum over A and B to 0 to infinity with arbitrary coefficients.
Yeah.
How do you know that you're going to end up with this?
With known coefficients, you know.
No coefficients. The A and B dependence is known, so we can just do the sum.
The
Right.
alpha are known?
What is not known here is OPE data. So this depends on OPE data and on A and B, and we know exactly how it depends on A and B. So this still depends on unknown OPE data here, but we can sum over A and B. So the OPE data of order k minus 1 fixes most or many residues of AK. So now, if we have a world
Yes,
sheet,
sorry,
yeah.
I have another stupid question.
Yeah.
The dispersive about the logic. So you use the dispersive sum rule comes from the OP data from the poles of MST, right? You open the contour, you get the poles, you get alpha as a function of those data.
Yeah.
But now it looks like you're getting back. So you're recomputing this poles and you're getting something new. Why don't we just get back a C squared delta L, which is the unknown that you started from?
I mean, we still have the same unknowns, right? We just expanded the OP data in lambda. Or?
Yeah, but what's different between taking MST, expand these poles in delta and write in the first form, the third formula you have on the blackboard with respect to, above the DSR, this pole of MST, you can take C square and expand as you did there and you get some formula. And here you have a different formula after you do a bunch of things.
Yeah.
But I would have naively expected that if you take that formula with C squared delta L with this expansion and you do the Borel transform, you land directly there without ever talking about dispersive sum rules. So I don't know, what did you learn from the dispersive sum rules and this sum?
Yes. Yeah. Yeah,
If it works, or isn't it just much simpler? Like never do any sum?
I mean, it's very easy to do the Borel transform for the polynomials. So yeah, we never.
Okay.
And also previously we worked more with the Wilson coefficients. Now we kind of bypass the Wilson coefficients by working with the residues.
Okay,
So
thanks.
You could probably do it, yeah.
Poles also due to the descendants. So it has many poles close to each other if we think in terms of square root of lambda. But with this Borel business, all the tower of the descendants condenses into a single pole. This is what happens in the flat space limit. And so since we wanted to study these layers, it was good to keep taking these Borel transforms because we did not want to deal with this condensation. Okay.
Okay, so now we want to see how we can compute the residues also from the worldsheet formula. Yeah.
So this Borel business, it's not necessarily related to flat space, right? It's something I could always do. Take the Mellin and Borel transform it, and I get another function of this capital S and T, right?
Yeah.
And like João said, so we know some things about the analytic properties of Mellin, but now João is saying that all these painful descendants, they become just a single pole in this Borel.
Yeah.
So would one say that Borel has nicer analytic properties and it should be the object that people should study, or?
Yeah, for this large lambda expansion, I think so, yeah. We have to sum all the descendants to get this, right?
But does it depend on being at strong coupling, or it's generic? If you Borel transform a generic Mellin amplitude, you get nicer properties.
I mean, it has to do with the pole of the pole of the Mellin amplitude has this lambda to the 1/4. So at large lambda, all the poles condense at infinity, and we get rid of this with this Borel transform. So we separate the poles. If the dimensions are finite, I don't think if it helps. So it has to do with the flat space limit, I would say. So how do we go from the worldsheet to the residues? So let's assume we have some integral with some arbitrary insertion of a multiple polylogarithm. So now the poles at S equals 1 to whatever at integers come from the region where Z is close to 0. So to compute this, we can use polar coordinates around 0 and expand in small rho. So then the poles come from such integrals where we have rho to this power. And then in the expansion, we just have powers of rho and logarithms. Squared. And then this integral just gives 1/2 and a pole of order p plus 1 plus regular. So this shows us that now, in the beginning we said we want multiple polylogarithms of weight 3k. And now we see that there is one such multiple polylog of weight 3k, which is the one with 3k zeros, which is just a log to the 3k of absolute value z squared. And this gives us the poles that are predicted by the dispersive sum rules. So this gives a pole of order 3k plus 1. So we see in this way that already it starts to match. And now we can make an ansatz for the worldsheet correlator and match the residues with the ones from the dispersive sum rules. So the worldsheet. So we make the following ansatz. AK. So we expected, we make this crossing symmetric ansatz. Where BK is given by this integral. And then here GK without the total. And now what are the properties of this G? Yes, S plus T plus U is 0. Properties of GK. One is it is transcendental. It has the transcendentality is 3K, and this is achieved by using single-valued multiple polylogs of Z and explicit single-valued multiple zeta values. Then by comparing to the low energy expansion, there, as I told you, a few of the Wilson coefficients are known, so their transcendentality is known. We can see that this should have homogeneity 2k minus 2 in S and T. And furthermore, to make it fully crossing symmetric, B should be symmetric in exchange of S and T, which means that G has to be symmetric under exchange of S and T and Z and 1 minus Z. So GK equals GK of T as 1 minus Z. So to implement the last symmetry property, we define the following combination of these polylogs. So we make them either symmetric or antisymmetric, and Z goes to minus 1 minus Z. And we also make them symmetric under exchange of Z and Z bar, because we expect the worldsheet correlator to be a function of ZZ bar and 1 minus Z bar, so that should be symmetric under exchange of Z and Z bar. And then we have to check, we can now go to k equals 1 and check how many of these functions are independent for weight 3. So for k equals 1 we have a basis where we have 4 of the L plus and 3 of the L minus. And then our solution looks like this. It's like of the 4, so the symmetric ones have to be multiplied by symmetric functions of S and T, and these ones by anti-symmetric functions of S and T. And here, one of these coefficients is 0, so we have 3 symmetric ones. and the antisymmetric ones are multiplied by this function. Okay, so this is the solution for G1. And then for k equals 2, we have the following basis. We have 25 symmetric ones and 20 antisymmetric ones. So now we have in the answers much more coefficients, and to fully fix the answers, we have to impart one conformal dimension, which is we need to the conformal dimension 1, 0, which is Konishi. So for higher values of k, we expect it to work in the same way, and hopefully it's enough to input a few dimensions of Konishi-like operators where the dimensions are known. K equals 0, what? K equals 0 is flat space, so it's what I wrote in the beginning. Yes, so G0 is 1/3 1 over u squared. Okay, so what are our checks? So we can compute the OBE data, and the OBE data that we compute is always averaged over the degeneracies that I wrote earlier, because we can just resolve the delta and L dependence. So for like the OBE data for k equals 2 are the averages c squared 2. Then the flat space C with delta 2, and flat space C with delta 1 squared. And these dimensions are known on the leading Regge trajectory from integrability, and they match for the whole Regge trajectory. And by the way, this has the form, it has some zeta 3 squared plus zeta 5 plus zeta 3 plus rational. This one depends only on the zeta 3, and this one is just rational. And we can also compute the Wilson coefficients. For any A and B. And here we have 2 checks. And here we also have 2 checks from localization. And by the way, it's clear from this kind of ansatz that both the Wilson coefficients and this average OBE data can only depend on single-valued multiple zeta values times rational numbers. This is because from this you can derive a general formula for the low energy expansion coefficients. Okay, so I think it's time to wrap up. So we found a way to determine the ADS Virasoro-Shapiro amplitude, order by order in alpha prime over r squared. And the main ingredients were that the worldsheet correlator should be a function of single-valued. There should be a single-valued function, and in particular should be have uniform transcendentality and be written in terms of single-valued multiple polylogarithms. And we used dispersive sum rules to input the condition that the correlator should be Reggie bounded, which is an important property of string scattering amplitudes. Yeah. So some future directions would be to apply this to other models. And I'm particularly interested in open string examples, because in flat space there are many relations between open and closed strings, like KLT relations and the single valued map that maps open string to closed string amplitudes. And yeah, it would be interesting to hear if somebody knows if this if there's an example where similar strong coupling anomalous dimensions are known for open string examples, because it's always important to have these checks in the end when you make all these assumptions. Of course, it would be also important to try to reproduce these results from a real string theory computation. So apart from the metric contributions I discussed, there should be, of course, also corrections to the vertex operators that can probably be handled by using pure spinor formalism. And also Ramond background flux should play a role. So, yeah. Thank you.
Can you say again what the relation was between the Borel transform and the flat space limit?
If you do the Borel transform and then take the ADS radius to infinity, then you get the flat space limit.
So meaning just keeping the first term in the 1 over lambda expansion of the Borel transform?
Yes.
Okay.
If you take the integral in the integrated correlator that's related to localization, does that integral converge when you're expanding the correlator away from flat space as you're doing? So like, I've got your notation. I think you're calling it G1, G2. So like, if you like, does the integral G1 converge? I guess part of the reason I'm asking is that I guess in principle, if you computed all the G's, then the integral of all those G's should equal, I guess, the planar limit of the localization result for finite lambda. So I'm wondering if you can kind of get close to that by integrating one by one, or if it's just not even convergent.
Yeah, I haven't checked. Yeah, by taking this G0 or G1, it's a different slice than what you usually do in the Mellin amplitude, right? Yeah, I haven't checked that.
Yeah, I think I missed something, because I thought your ansatz would be like numbers times this L plus and minus and zetas. But how can you get like a function dependence in S and T in front of the L's?
So the G has to be homogeneous of degree 2k minus 2 in S and T. So rational, yeah. It's like what we do is we assume that the denominator is U squared, because it's whatever you put in the denominators will be poles of the amplitude, and you cannot put some weird functions. You can also put a more general denominator, and then you will get ambiguities in the form of G, but they will not be ambiguities of A. So there are ambiguities in G that lead to terms proportional to S plus T plus U in A. So they vanish for the amplitude, but so if you have, so this integral without the insertion has a pole at S equals 0 and T equals 0, and is 0 at U equals 0. So it's quite natural to include a 1 over U squared. But here it turns out the 1 over U squared cancels. And in this case also, in the symmetric part, you don't need a denominator. And in the antisymmetric part, you also get this denominator. So we used an ansatz more general than what's necessary to find a solution.
So can you comment a bit on why do you think that you could really keep pushing it and go to higher orders in K? I mean, in n equals 4, there are often things that work well at 1 loop and 2 loops, but then it's hard or impossible sometimes to follow the same strategy. So K equals 3 and 4, you could do as well?
I mean, we haven't tried. We thought k equals 2 is enough, like, to claim that it should work. I mean, I don't see what should change. So,
but can you at least count parameters and see how many parameters would you need to input for k equals 3 and how many for k equals 4?
yes. The problem is when it's hard to estimate how many of the parameters are fixed by the dispersive sum rules, because eventually you land on a solution and it just stops fixing things, right? So I don't know a priori how to, I can count how many parameters there are, but I don't know how to count how many will be fixed by dispersive sum rules.
As I was commenting at the beginning, I do suspect the qualitative change when k is big enough, because one could argue that from the point of view of effective string theory, everything at the sufficient low value of k is fixed by non-linearly realized target space super isometry. Right? But once you go to high enough k, you need additional recipes like integrability to pin down those ambiguities.
Okay.
Just another comment. I think this would be quite interesting to reproduce this G1 from the direct worksheet calculation. It may not even require pure Springer formalism. It might be possible to do NSR formalism, but just by starting with the 4-point function and insert, Raman vertex operators, like it's quite conceivable that these multi logs can be reproduced in that way.
Yeah, that would be very interesting. Yeah.
Did you try or do you expect a similar formula for the higher P? You looked at O2, O2, O2. If you look at other BPS operators, P1,
yes,
P2,
we
P3,
did it for 2,2 pp, and yeah, it also works. You can do it.
So what changes in this type of?
Mostly, it's not fully crossing symmetric, so you have to use a different dispersive sum rule, because now you expand in something like S to the A, T, U to the B. So you need to use a different dispersive sum rule.
But then here at the level of G0, G1, it's just you have some P's appearing.
Yeah,
and
everything becomes functions of P. Yeah.
Okay. Thank you.
Any more questions? Okay, then let's thank Tobias again for the nice talk.
Thank you.